Okay, folks, so I want to pick up with the direct substitution property, which is going to be something that allows us to easily evaluate uninteresting limits. Okay? So what we will see is that for a polynomial or a rational function, okay, remember polynomial functions? Rational functions are just quotients of polynomials. Okay? And I guess we could also add to this, or root functions. We could add to that. Okay. If f is a polynomial or a rational function or a root function, and then this seems silly for me to make you write, and a is in the domain of f. Does everyone know how to read this? Read this expression here. A is in the domain of f. That's what I'm saying there. The reason why I made everyone write the word and there is because a lot of you are going to think, oh, I can use the direct substitution property everywhere. No, you can't. In fact, most problems, when I initially give it to you, you will not be able to use the direct substitution property. Okay? This doesn't solve all your problems. Okay? But if it's a nice, well-behaved function, a polynomial or a rational function or a root function, and the limiting value is in the domain, then rather than evaluating the limit, we can just evaluate the function at that point. The graph of sort of what's going on here is for these rational root and polynomial functions and a lot of other ones, is they're well behaved. The fancy word that we're going to give later on is they're continuous. Okay? And so if I say what's the limit as x approaches a, well, that's kind of an ugly graph. Let me fix that. So if I say what's the limit as x approaches a, if it's a nice, well-behaved function, continuous, like this, then figuring out what the limit is the same thing as figuring out what the functional value is, right? So this is the ordered pair a comma f of a, right? And what do we see? We see that f of a agrees with L, the limit. So the direct substitution property says rather than evaluating the limit, you can just plug the limiting value into the function. Okay. Does this always apply? No, it does not. All right, we got to ask that again. Does the direct substitution property always apply? No. No. I need a resounding no on that. Does the direct substitution property always apply?
No.
No. Oh, I like that. Okay. But if it's a well-behaved function, and the limiting value is where? In the domain, then the direct substitution property applies. Okay? Unfortunately, too many people learn the direct substitution property. They do some easy questions with the direct substitution property, and then they start applying it everywhere. Okay? So let's try to nail this right away. Okay? Let's look at 8 and 9. Okay? These two problems are completely different problems. These two problems are completely different problems. And I need you to see them as being completely different problems. 8 is kind of a fun little question. I will ask maybe one of those on your test. 9 is the more typical question. Okay? Let's look at 8. Okay? What's our function here? F of x is equal to what? What's our function? Yeah, right? What's the domain of f? That's the domain, right? What's our limiting value? What is 0 in relation to the domain? It's in the domain. We've got a nice rational function, and where is 0? It's in its domain. So if I'm asking you to evaluate this limit, this is all you have to do. To find the limit as x approaches 0 of x squared minus 1 over x squared, over x minus 1, all you have to do is apply the direct substitution property. Just go ahead and plug in the number 0. What do you get when you simplify that? 1. Now, this is very important. You don't have to write this out for me, but it needs to be completely apparent to me what you just did. What did I do from this line to this line? Why?
Direct substitution.
Yeah, that's what I'm looking for. I applied the direct substitution property, right? What did I do from here to here? I applied the direct substitution property. I don't have room to write that, but if I did, I would write, well, let me see, do that. Apply the direct substitution property. Okay. How is it apparent to me that that's what you did? Well, what did you write before that? A limit expression. What did you write after it? Just an expression. So I know what happened there. Okay? That's why you have to be writing that limit every single step of the way up until then. Right? Okay. I will not ask many questions like number 8. How come? Because it's not, there's no math involved. It's just, it boils down to just an algebra question. Plugging something into a function. We're not learning anything new. Okay? The real way to look at it is, this function isn't very exciting at 0. So evaluating the limit at 0 doesn't really give us any new information. Okay? Let's look at number 9. We've got the same function here, right? Here a, though, is equal to 1, and what is 1 in relation to the domain? Yeah, 1 is not in the domain of f. Can I apply the direct substitution property to this problem? No. I cannot apply the direct substitution property here. So what do? We look at the limit as x approaches 1, and what did we do when we encountered something like this before? Yeah, we tried factoring it. Let's see if that trick works again. We get x plus 1 times x minus 1 all over x minus 1. As before, the x minus 1s divide out. So we're just left with the limit as x approaches 1 of what? X plus 1. What is x plus 1? It's a polynomial function. It's a well-behaved function. What's the domain of any polynomial function? All real numbers. What's the limiting value? 1. That's a real number. So I can apply the direct substitution property to this. So what do? Now I can write this as 1 plus 1, and I get 2 for the limit. Okay. The bulk of these problems boil down to doing some algebra until you can apply the direct substitution property. That's what the bulk of these problems boil down to. Now the algebra you have to do gets harder and harder. Okay. Let's do, so now at this point we got a lot of tricks to cover. These are all old algebra tricks. Okay. So if you look back at an algebra textbook and you see what problems they had you do, they were all problems getting you ready for these types of limit problems. Stuff like you did rationalizing denominators, multiplying by conjugates, factoring and reducing, all of those were skills getting you ready to be able to evaluate these limits. Okay. How do you explain that to somebody in Algebra 1? Right? Okay. But this is why, they had a very good point. Why on earth am I multiplying by a conjugate? Who the heck cares? Well, now we care. But they had a good point. All right, let's look at this problem here. Does the direct substitution property immediately apply? No. Take a look at that. Always. It will usually never immediately apply. If it does, then we're asking too easy a question. Okay? All right. So here's our trick. Last time we factored to clean things up. What are we going to do here? In this problem, I'm going to expand to clean things up. I'm going to FOIL this out as 9 plus 6x plus x squared minus 9 all over x. Everyone see what I did there? Amy, how are we doing?
Didn't see what you did.
Yeah. So let me FOIL this out. So this is 3 plus x squared, which is 3 plus x times 3 plus x, and now we FOIL it out. So we do our first. That gives us 3 times 3 or 9. Our outers gives us 3. Sorry, I said first.
I'm catching it now.
Yeah, all right. I don't remember how to FOIL. There we go. That's what you get. Okay. I remember how to FOIL. I don't remember the acronym. Okay. All right. Sometimes I remember how to FOIL. Let's clarify that. All right. So what happens to the 9s up there? They add out, which isn't really apparent why that's helpful, but look at this now. Now what can I do? Yeah, let's factor out an x. Folks, are you still writing the limit each time? Come on, I'll split profits with you. Let's use as much lead as we can. Okay. We get x times 6 plus x all over x, which gives us the limit as x approaches 0 of 6 plus x. Now, at every step up until here, could I use the direct substitution property? No. Now, I can. What does this give us? This gives us 6 plus 0, which is 6. Okay. So you're building a list of tricks here. Folks, you're going to have to get so familiar with these limit problems that you can look at it and know which trick you're supposed to apply. In the previous question, the trick was to immediately factor. In this question, before we did that, we expanded and cleaned things up, and then we factored. You got to practice them all. Let's do some more tricks. I'd like to evaluate this limit. What's preventing me from using the direct substitution property? The x squared in the denominator, right? Because this function is not defined where? At x equals 0, which is precisely my limiting value. So we need to have something happen. I would like to cancel that x squared out of the denominator, right? I would like to divide it out somehow. We can't just wish it away, right? So let's try this trick. We've got an x squared in the numerator. Let's try to get it out of the square root somehow. Can I just pull it out? Okay. Let's put this to bed right away. Does this equal this? No, it does not. You cannot distribute a square root over what operation? What operation is that? Addition. Can you distribute a square root over addition? No. Now, if I gave you this, does x squared, or does the square root distribute over multiplication? Sure. That does equal 3x. That is true. That is dead wrong. Okay. So, folks, this is where people got into trouble in algebra, right? You learned one trick, like, oh, I can distribute a square root over here, over multiplication, and then you tried to apply it in the wrong place. Okay? So be careful, folks. Okay? All right. Any questions on that? All right. So my problem still remains the same, though. I'd like to somehow use that x squared in the numerator to cancel with the x squared in the denominator, if I can. Nothing saying I can. Let's try this. Okay. One way to get rid of radicals in a place is to multiply by the conjugate if it's a binomial. Okay. So what am I going to do? I'm going to take this expression here. Let me write it down here. The limit as x approaches 0, I've got to keep writing that limit, okay, of x squared plus 9 minus 3 all over x squared, and I'm going to go ahead and multiply this by x squared plus 9 square rooted plus 3 all over the square root of x squared plus 9 plus 3. Folks, am I allowed to just multiply an expression by any number I want? No, I'm not, right? So if I had the expression 4, can I say that's equal to 4 times 3? No, of course not. What number could I multiply 4 by? 1. What if I really want a 3 right there? What could I do? I could write this as 3 over 3, right? That gives me the 3 that I want, and I haven't changed the equality. I haven't changed the weight of the expression. Okay? So I wanted to multiply the numerator by the conjugate of this expression. Notice that the conjugate is the exact same binomial, but the sign of the binomial changed. It's the same. So if I have the expression a plus b, what's its conjugate? A minus b. It doesn't matter what a is. It doesn't matter what b is. To take the conjugate, you just change the sign of the binomial. Okay? So the trick that we're using is we want to multiply this expression right here by its conjugate. We'll see why that works in just a second. But I can't just multiply an expression by any old number. I can only ever multiply it by what? 1. Somebody once told me that most of math is adding 0 and multiplying by 1. I agree. Almost all the tricks we do are multiplying by 1 or adding 0 in some clever way that gets us where we're going. Okay? So this is just the number what right here? 1. Okay. I'll FOIL this out on the previous page, next page, because I'll run out of room here. Okay. Okay. So I'm going to go off to the side and just compute this part right here. I'm going to do this numerator product, x squared plus 9 minus 3, and I'm going to multiply it by the square root of x squared plus 9 plus 3. All right, I'm going to do this once slowly. Okay, I'm going to do it once. I'm going to show you all the work. Okay, if you ever get stuck, you come back to this work. I will usually FOIL this out in my head, okay, because I prefer it that way. I make mistakes when I do it slowly. Okay, so how do you FOIL something? I don't remember the acronym. We're going to multiply this times this. Okay? So we do the square root of x squared plus 9 times the square root of x squared plus 9. True? Okay. Then we will do, I think we called it the outers. Okay? So then we'll do plus 3 times the square root of x squared plus 9. Then we will do the inners. What's the inners? Minus 3 square root of x squared plus 9. Then we will do the last, and we will get minus 3 times 3. Okay. Are there any questions on this? Any questions, folks? All right. Why on earth did I do this? I did it for 2 reasons. One, I wanted to get rid of the square root. I guess that's the only reason. I wanted to get rid of the square root. What is the square root of something times the square root of that same expression? It is just that expression. So this leaves me with x squared plus 9 right there for simplifying this expression. Any questions on that? Okay. Now, why does multiplying by the conjugate just not make the problem more complicated? What happens to my outers and inners? They cancel. They reduce. They add out, right? Will that always happen?
Yes.
Yeah. When you multiply by a conjugate, it will always happen. That's why we multiply by the conjugate. That's why we do this trick, is we get rid of the square roots if there are any, but we don't make things more complicated because the outers and inners always cancel. Why do they always cancel? Because they will always have the opposite sign. Why will they always have the opposite sign? Because they're conjugates. Right. And then we get minus 9. That's the wrong color. And we get this right here, which is minus 9. That's for this term right here. Okay? Yeah. So I will usually just do that in my head, folks. Okay? Why? Because it works the same way every time. So I don't even actually think about multiplying it out. I just say, okay, it gives me that expression minus the product of those two. So let's do it. Oops. There we go. So when I multiply by the conjugate, what do I get? In the numerator, I get the limit as x approaches 0 of x squared plus 9 minus 9. That's what we just showed. We just took some time to show that. Okay. Any questions on that? Now, folks, it breaks my heart because some people get so excited about multiplying by the conjugate, they just drop the denominator altogether. I can't tell you how many times people, they're doing all the correct work and then they just forget the denominator. Okay? Don't forget it. I don't know how to say that any other way. A fraction needs a denominator. Okay? So this leaves me with then x squared times the square root of x squared plus 9 plus 3. Okay, and I'm not going to worry. I could distribute that x squared if I wanted to, but having done this 60,000 times, I'm not going to distribute because it doesn't help me. Okay. All right. We're left with, though, just the limit as x approaches 0. Here I'm going to run out of room, so I'd like to just write that that's going to be 1 over the square root of x squared plus 9 plus 3. What happened? First of all, the plus 9 and minus 9 added out, right? So that left me with x squared over x squared times this expression. But then the x squareds divide out, right? So I get 1 over just that expression. Okay. Now, what do we got? We've got a function that involves, it's not really a rational function because technically rational functions can't have square roots, but it's a root function that looks like a rational function, right? It is, let me just say it, I'm going to start using this word, we'll define it later. It is continuous everywhere it's defined. It's well behaved everywhere it's defined. Is 0 in the domain of this expression? If I plug in a 0, do I violate any rules of math? No. So let's go ahead now and apply the direct substitution property. Where did my limit sign go? Away. I stopped writing it because I did what? I applied the direct substitution property. Folks, did you write the limit every time up until then? All right. We end up with, once everything clears, 1/6. I do not think that there's a way you could, well, there are ways. But generally, I don't think you would look at this problem and ascertain that that's what the limit is. And I think you'd even have a hard time doing the plug-in numbers, right? Unless you're very good at spotting the decimal equivalent of 1/6, I think you'd have a really hard time even using that table of values approach. Any questions on that trick? All right, all of the above properties, that's kind of what you'll watch in the video, extend to left and right hand limits. So specifically the direct substitution properties applies to left and right hand limits, and all of the properties that you'll watch in the video. Okay? So, I now want to find the limit as x approaches 0 of the absolute value of x. All right. Everyone raise your hand and solemnly swear not to wish away an absolute value. Okay? This is what people do. They say, oh, absolute value makes stuff positive, I'll stop writing it. I see that in students' work all the time. Absolute value makes stuff positive, I'll stop writing it. You can't just stop writing it. Okay? Now, let's give the definition of the absolute value. Okay? What is the definition of the absolute value of A? What's the absolute value of 4? 4. What did you do to the number 4? Nothing. You left it alone, right? What function leaves something alone? Just the identity function. Okay. When do you do that? You do that if A is greater than or equal to 0. Okay. What is the absolute value of negative 4? 4. Don't say you made it positive. What did you do to that number? You changed the sign on it. Multiply by negative 1. That works. You changed the sign on it. You didn't make it positive. You changed the sign on it. Okay? So how do I change the sign on the number A? put a minus sign in front of it. That's if a is less than 0. So for example, if I said what is the absolute value of x plus 2, if you want to, you could split it up into two parts. You could split it up to be, it's just x plus 2. Oh, I'm going to run out of room there. What's the absolute value of x plus 2? Well, it's just x plus 2 if x plus 2 is greater than or equal to 0, right? Does everyone see that follows immediately from what we did above here? Okay, so I'm going to start using this term, argument. The thing inside the absolute value is called the argument. If the argument is greater than or equal to 0, you leave it alone. If the argument is less than 0, you change its sign. What's the thing inside the absolute value? X plus 2. If the argument is positive, you just leave it alone. What if the argument is negative? What if x plus 2 is less than 0? What do you do to it? Don't say make it positive. Change the sign on it. Negative x plus 2. Everyone see what we just did there? I will test you over that, at least twice. I will find ways to test you on that. Now, if you want to, you could solve this inequality right here, right? X plus 2 is greater than or equal to 0. That happens when what? X is greater than or equal to negative 2, right? And when does this happen? This happens when x is less than negative 2. And that should fit, right? If I plugged in a negative 5 for x, I would have negative 5 plus 2, which is negative 3, and the absolute value of negative 3 is 3. That's the same thing as putting a negative sign. That's the same thing as saying negative 5 plus 2. What does that come out to be? 3 as well. Okay. All right, that's how you work with absolute values. Okay. So now let's do some limits with absolute values. All right, let's show that the absolute value, let's show that the limit as x approaches 0 of the absolute value of x is 0. Okay. Well, I can't find the limit proper. I don't know how to find the limit proper of this problem. So what should I break it down to? What's that?
Approaching from the left and the right.
Let's approach from either direction. So let's first approach from the right. Of the absolute value of x. Now, what types of numbers am I plugging in for x? Only positive numbers, right? So now there's no ambiguity. Even though I don't know what x is, I know that it's positive, so I know how to take its absolute value. How do you take the absolute value of a positive number? Everyone say, leave it alone.
Leave it alone.
Very good. The limit as x approaches 0 from the right is just x, right? Now, this is very important. What did I do to make this argument? I looked at the definition, right? I looked at the definition to do that. Did I just wish away the absolute values? No, I went to the definition and applied the definition to it. What is this function right here? It's a nice polynomial function. How can we evaluate limits of polynomial functions? With the direct substitution property. No work required. We just say that that's equal to 0. What did I do? I replaced the x with the limiting value 0. That was one way. We approached from the right. Now we need to look at the limit as x approaches 0 from the left of the absolute value of x. So what is the sign on the argument going to be? The sign of the argument, the sign of the stuff inside the absolute value is going to be negative. How do I take the absolute value of a negative expression? Change the sign on it. Okay. So this is equal to, in fact, well, that's fine. Limit as x approaches 0 from the left of negative x. What did I do? I just changed the sign on all of the stuff inside the absolute value. But what is the function negative x? It's a nice polynomial function. What can we apply? Direct substitution property. This is equal to negative 0, but what's negative 0? It's 0. Now, my question wasn't to find the left-hand limit and the right-hand limit. What was my question? To find the limit proper. Therefore, what's the limit as x approaches 0 of the absolute value of x? 0. How come? Because the left-hand limit was 0 and the right-hand limit was 0. I'm a stickler for that problem. I feel like if you can learn to be careful with that problem, you learn a lot. Unfortunately, though, the answer is always 0, so students kind of just, oh, I could do that. So I then give them a little bit harder one, where the answer is a little bit more difficult to determine what it's always going to be. So here I ask you to prove that the limit as x approaches 3 of this expression does not exist. Okay? So I want to look at the limit as x approaches. I wish I could just look at the limit proper, but what's in here? Absolute value. So I'm probably going to have to do left and right hand limits. Okay? Let's pick the right hand limit. Absolute value of x minus 3 all over x minus 3. Notice, of course, I can't use direct substitution because I don't have a nice polynomial or rational function, right? The direct substitution property does not apply to absolute values. What types of, this is where it gets a little bit trickier. What types of numbers am I plugging in for x? Numbers just a little bit to the right of 3. Numbers like what? 3.14, 3.1. When I subtract 3 from that, what will I always get? A positive number. Does that make sense? Everyone understand that? This is very important. As I approach 3, but from the right, the argument of the absolute value will always be positive. How do I take the absolute value of a positive expression? Leave it alone. We get the limit as x approaches 3 from the right of, and here just to emphasize that I did something, I'm going to put it in parentheses. You don't have to put it in parentheses, but that just emphasizes that I applied the definition of the absolute value. Did I wish it away? No, I made a decision based upon the definition. Okay. What does this expression simplify to? This gives us the limit as x approaches 3 from the right of just 1. What is the limit of a constant? It is just the constant. Let's go the other way. Let's now look at the limit as x approaches 3 from the left of the absolute value of x minus 3 over x minus 3. I'm now approaching 3 from the left, which means I'm plugging in numbers like what? 2, 2.5, 2.9, 2.99. All of those numbers, when I subtract 3 from them, what do I get? A negative quantity. In this case, when we approach 3 from the left, the argument inside the absolute value will always be negative. How do I take the absolute value of an expression that's negative? Change the sign. So this gives me the limit as x approaches 3 from the left of negative x minus 3 over x minus 3. What does this simplify down to? Simplifies down to a negative 1. What is the limit of a constant? It's just the constant. Therefore, the limit as x approaches, where were we going? 3, of the absolute value of x minus 3 over x minus 3 does not exist. How come? The right-hand limit doesn't equal the left-hand limit. So you might see me make that statement there. RHL, or sorry, RHL, right-hand limit, LHL, left-hand limit. We found the right-hand limit. We found the left-hand limit. We showed they didn't exist. All right, folks, this will show up on your first exam, I promise. Different numbers. It'll show up on your first exam, I promise. There's a good chance it'll show up again on another exam. Okay? All right. Oops. Oh, that was that square picture. Okay. Oh, we got a little more time. Let's keep going. All right. This is getting at a subtlety. I think it's really important. Okay. Let's look at the limit as x approaches 3 from the right of f of x. That's the limit as x approaches 3 from the right of the square root of x minus 3. Oh, folks, you haven't watched the video yet. I didn't ask you to. We have a property that I've not yet told you. I am allowed to pass a limit through a square root function. There's a property that we'll talk about that says I'm allowed to pass a limit through a square root function as long as the radicand doesn't come out to be what? Negative. Well, what numbers am I plugging in for x? Numbers to the right of 3, like 4, 3.5, 3.1. When I subtract 3 from that, I will always get a what?
Positive number.
Positive number. Can I take the square root of a positive number? Yes. So I can pass this limit through the square root. Okay. Watch, and I haven't posted it yet. I'll get those videos posted later tonight. Maybe first thing tomorrow. I'm tired. I'm working on them. The video will explain that we can pass a limit through a square root. Okay. But now, what can I do with the limit part of this? Just apply the direct substitution property. So what does this give me? This gives me 3 minus 3, which is equal to the square root of 0, which is equal to 0. Everybody, square root of 0 is? 0. The limit as x approaches 3 from the left of f of x does not exist. Somebody explain that to me. Exactly. So what's the limit proper? It does not exist either. How come? Because the left-hand limit doesn't equal the right-hand limit, because it doesn't even make sense to talk about the left-hand limit equaling something because it doesn't exist. Folks, we are tackling all of these problems, I'm going to use this phrase, analytically. Okay, we're tackling all these problems analytically. And that's how you need to be able to tackle them. Okay? However, I think oftentimes a graph really helps. Let's look at the graph of this function. What is the graph of the square root of x minus 3? It's the square root curve shifted to the right 3 units. What's the limit as we approach 3 from the right? As we approach 3 from the right, what are the y values getting closer and closer to? 0. As we approach 3 from the left, we can't. Because values to the left of 3 aren't in the domain of this function. So the left-hand limit doesn't exist. So the limit proper doesn't exist. So we were working through section 2.3. I believe we did question number 15. Is that correct? Okay, so let's jump into 16 now. So here we've got a piecewise defined function. Is it defined for all real numbers? No, it's not defined where? At 4. So the domain of this, the domain of f, we could say would be from minus infinity to 4, union with 4 to infinity. But what's our question asking? So that what happens? Not f of x, not f of a, but the limit as x approaches a exists, right? So where can you take the limit for this function? Okay. Well, let's suppose a is less than 4. That's the first case I want to look at. Well, if a is less than 4, what's the limit as x approaches a? Well, let's go ahead and replace f with one of its rules. Can we do that? Yeah, because what do we know about the a value? It's less than 4. So we know which one of these two rules we get to use, right? Which one? Yeah, the second one. Okay. Well, what do we know about 8 minus 2x? Well, we know lots of things. It's a polynomial function, right? What's the domain of a polynomial function? All real numbers. So we can evaluate this limit by what? The direct substitution property. Okay? I'm going to say that one more time. This expression is defined for all real numbers. A is a real number. So we can go ahead and evaluate this limit through the direct substitution property, and we would find that it's 8 minus 2a. Not very exciting. Right? This function isn't very exciting for values less than 4. Okay? What if a is greater than 4? Well, we look at the limit as x approaches a of f of x. That's the limit as x approaches a of what? What rule are we going to use here?
Root x minus 4.
Yeah, the square root of x minus 4. Can I say with certainty that I can use this rule? Yeah, because eventually, what am I going to get close to? A. And what is a? A number bigger than 4. So eventually, I will only be looking at approaches close to something above 4. So I can certainly use this first rule. Okay? So then we can just go ahead and evaluate that. That's the square root of a minus 4. So we can certainly evaluate the limits if a is greater than 4. We can certainly evaluate the limits if a is less than 4. Who's left? 4. That's really the heart of this question. What about a equals 4? Okay. And just looking at this, I sort of knew that right away. Because this was defined, piecewise defined, and they were defined by nice well-behaved functions, either root functions, polynomial functions, rational functions, I knew that the limit would exist everywhere on the interiors. The question is, do these two functions join up nicely? Do the two pieces of this piecewise function join up nicely? That's what we're looking at here. So really, the only place where this could have fallen apart is at a equals 4. So let's look at that. So let's look at the limit as x approaches 4 of f of x. Well, this is what we want to find. But what? What's the issue here? I've got two different functions, two different rules I could possibly use. Does everyone see the problem? I can't start working with this limit because I don't know which function rule to use. So what should I do?
You gotta look at it from the left and the
Yeah, let's pick a direction of approach. Let's just pick one, and then we'll pick the opposite one, and we'll compare them. So let's look at the limit as x approaches 4 from the right for this function. That's the limit as x approaches 4 from the right of what? What do I get to do now? I get to pick my rule. Which rule? Yeah, the square root of x minus 4. What do we say here? Well, root functions, we said, obey the direct substitution property. So we can evaluate this through direct substitution, and we get 4 minus 4 equals 0. So everything's riding on what? if the limit's gonna exist at 4, we're gonna take the left-hand limit, and for the limit proper to exist, it better also be what?
0.
0. Well, let's find out. So we look at the limit as x approaches 4 from the left of f of x. Because we're approaching from the left, we get to know which of the two pieces we want. We'll use the second rule. So this is 8 minus, I think it was 8 minus 2x, is that right? But this is a polynomial function, so we can evaluate it through direct substitution. So we get 8 minus 2 times 4, which is also equal to 0. So the left-hand limit equals the right-hand limit at a equals 4. So where can we find the limit for this function? The limit for the limit as x approaches a is certainly 0. That's true. Or excuse me, the limit as x approaches 4 is certainly 0. But the question was, where can you take limits for this function?
Everywhere.
All real numbers. So we can find limits on minus infinity to infinity. So even though this function wasn't defined someplace, we can still find limits everywhere for this function. Okay. All right. This next theorem is not a very, it's a sort of useful theorem, but we're going to really use it as a building block for a more important theorem. Okay? So we're not going to prove it, but we'll just talk about it. By the way, I use this symbol here. This symbol here, I write as sort of an upside down A. This symbol means for all. Okay. So how would you read this? You say, suppose f of x is less than or equal to g of x for all x near a, around the value a, around the limiting value. Okay. So one thing I think you should encourage yourselves to start doing is, if you read an expression involving f of x and it doesn't make sense, see if you can give a different interpretation of what f of x is. What type of value is f of x? It's a range value. So if the range values of f are always below the range values of g, what can we say? If the range values of f are always at or below the range values of g, what can we say? We can say that the limit as x approaches a of f of x must be what in relation to the limit as x approaches a of g of x? It also must be less than or equal to. Okay. By the way, we did assume that the limits all existed. Okay, that statement was gonna. This isn't a real important theorem. I'm not gonna hold you accountable for this, but we need it for the next one. All right. This is called the squeeze theorem, unless you haven't had dinner yet, in which case you call it the sandwich theorem. Okay, another name for it. And it says, suppose you have 3 functions. Okay, and just kind of spilling the beans right now. We're interested in talking about g of x. Suppose g of x is trapped in between f of x and h of x. What can we say? Well, it depends. It depends on how f of x and h of x behave around the limiting value. Okay? So the squeeze theorem says, suppose f of x is always below g of x, which is always below h of x. Then, if the limit as x approaches a of f of x is L, and the limit as x approaches a of h of x is L, then the limit as x approaches a of the inner function must also be what? L. So here's a picture that goes with this. Okay. So suppose let's see, I think I called the lower function f of x, and I called the upper function h of x, and the crazy function that I'm trying to work with is g of x. So notice that g of x is a very erratic function, right? It's doing that rapid oscillation that we've seen in a couple of examples. You might have some trig components. It might be really hard to pin this function down and try to do analysis on it. But notice that eventually the yellow function is always above the red function. And eventually the yellow function is always below the blue function. And this part's critical, what is the limit as x approaches a of the red function? It's L. And what's the limit as x approaches a of the blue function? It's L. So what can we conclude? The limit as x approaches a of the yellow function must also be what? L. Do you understand why we call it the squeeze theorem? Or the sandwich theorem? Okay. It's trapped in between those two. Okay, so let me give you an example of how we use the squeeze theorem. Okay? To be honest, usually if you're going to use the squeeze theorem, it requires some ingenuity. It requires a little bit of creativity for finding out a way to apply it. Okay? I generally won't ask you to do a squeeze theorem question unless it's one that I walk you through in the steps of the problem, or I've already showed you this trick before. Okay? Because I'll show you the trick for this one in a minute, and you might say, who thought of that? Well, I don't know. The textbook guy did, right? Okay. By the way, we looked at a function similar to the sine of 1 over x. Okay? And what did this function look like? Well, it looks like this. It went something like this. Right? You remember that one? That was our first example of a function whose limit did not exist where in this case? 0. We said the limit as x approaches 0 of the sine of 1 over x does not exist. And the reason why was because it was oscillating too rapidly. It was never approaching a fixed y value. The closer you got to 0, the more rapidly it jumped up and down. So it was never approaching a fixed y value. Okay? So you might think, I think it'd be a good guess to think that this limit doesn't exist either, because that sine of 1 over x is so erratic. But it turns out it does exist. All right. So I can't work with this algebraically. I mean, if I could, my goal would be to maybe, by using some sort of algebra, get this 1 out over x, which is the problem. It's the thing that's preventing me from doing direct substitution, and somehow cancel it with something else. But I know of no way to do that. Okay. So now we need to be clever. We got to come up with something, outside the box. And the answer to doing this is let's use the squeeze theorem. Okay? So I'm going to start off with a fact. Okay? It's a true fact. I think you'll all agree with it, but you won't necessarily know why we picked it. Okay? What's the range of the sine function? What's the output values of the sine function? Yeah, they go from -1 to 1, right? So even though this function is very erratic, the y values still jump back and forth between -1 and 1. This is, of course, for x not equal to 0. Excuse me. Which is, I think we would all agree to that. That's a true fact, but how does that help us? Well, here's the clever move. Let's multiply all three sides of this inequality by x squared. So that gives me -x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. So in the functions we were working with before, this will be our f of x, this will be our g of x, this will be our h of x, and this will be the g of x, the one that's difficult to get a handle on. Now, for the squeeze theorem to work, it's not enough to show that our function that we're working with is between two functions. That's not enough. We've got to show that these two functions converge to the same y value at the point that we're interested in. Okay? Well, let's just check. Okay? Let's take the limit as x approaches 0 of all three sides of this inequality. And that's using the theorem on the other side, the previous page, the one I said was incredibly important. Okay, does everyone see what I just did there? Took the limit of all three sides of this inequality. Does this help me? Jimmy, what's up?
Yes.
Yes, how come?
You can find, you can direct sub the left side of the inequality.
Okay, so that's going to be 0, right? That's going to be less than or equal to our answer, if our answer exists. But what's the limit on the right-hand side? It's also 0. So now we know that our limit exists because it's trapped between two finite numbers that are the same number. So it has to exist, and in fact is what? Therefore, the limit as x approaches 0 of x squared sine of 1 over x must equal 0. We trapped it. We trapped the answer. Right? We didn't find it. We trapped it. That works by the squeeze theorem. Okay. Any questions on that, folks? Okay. So, I think that's a particularly challenging question until you've seen it done for you. Right? I don't think you would say, aha, let's start off with this agreed upon fact. Okay? And then try to come up with some way of pinning this function between two other well-known functions. Although, if you were to look at the graph of this function, it might give you a hint as to how you could use the squeeze theorem. Okay? So if you've got a little bit of room, let's go ahead and graph this function. Okay? It turns out the graph of this function looks like this. Just like before, it starts oscillating incredibly rapidly, and it's undefined at 0. And it's oscillating incredibly rapidly. But unlike the last example, it's oscillating incredibly rapidly, but the amplitude decreases here. And the amplitude decreases fast enough that we're able to pin this thing. So you can see from the graph, it appears that the limit as x approaches 0 of this function is 0. And sure enough, it's true, but proving it is tough without the squeeze theorem. Okay? But I think if you look at your graph, these are quadratic asymptotes. We don't really deal with quadratic asymptotes. Okay? But this has quadratic asymptotes here, and that sort of gives you an insight as to why maybe you would try to bound this function between these two functions. Okay? Any questions on that, folks?